Hi, in this video, we want to take a look at two-way Anova. All right, so two-way Anova is the situation where we have multiple populations that are defined by two variables, and we want to check to see, do we have the same average for some variable that is measured on both of these populations. All right, so for all the different populations. So in one-way Anova, we've got one variable is like our independent variable, and then we have a dependent variable, our target variable. In two-way Anova, we've got two different variables, and we want to check to see, do these two variables create different populations in terms of that dependent variable over here. All right, now, anytime we do Anova, there is a strong relationship with regression. Anytime you do regression, there's a strong relationship with Anova. So, you know, there's something to keep in your mind as you work through these problems. All right, so once again, we are using example code from an introduction to statistics with Python. And here is the website to get the code that I'm copying and pasting. And the textbook is free to download from UCF's library. I keep on saying this in all of our videos because I don't want to get in trouble with copyright infringement. I'm hoping that they interpret this video as being free advertisement for them. All right, so whenever we talk about interaction, if I've got two variables and I look at the impact of one variable and on a target variable, and I look at the impact of another variable on the same target variable, well, there's times when if we put them together, we get a stronger or a weaker result than we do individually off of the variables if I have them in isolation. Okay, so that is the situation when we talk about interaction. Interaction means if we have an interaction term in there, if we have an interaction model, that means that putting them together, the two dependent variables together, results in a greater or a lesser result than what we would get from the variables individually if the other one was a fixed value. All right, so the data set for this is the measurement of fetal head circumferences by 4 observers in 3 fetuses from a study investigating the reproducibility of ultrasonic fetal head circumference data. Kind of interesting data. So let's take a look. All right, so first and foremost, I'm going to go through and I'm going to load the packages. So we've got NumPy. We're going to use the NumPy, Pandas, URL library. All right, we're going to use that to download the data from the author's website. So that's right here. Now here we're going to use stat models to get ordinary least squares. Ordinary least squares refers to regression. And then we're going to also, from stat models, we're going to be getting the Anova underscore LM. That LM stands for linear model. So we're talking, so you can see that this code is bound up in regression pretty tightly. Let's go ahead and load that. All right, now what we want to do, we want to load the data. So what we're going to do is we're going to take the URL. So here I've got HTTPS, all this stuff here. So here, this is where it's stored. We can see that it's stored at raw.githubcontent.com, and then the author's site. Then it becomes more specific. And then I've got this in file. Here's the actual name of the file itself. You'll notice that it's a text file. All right, well, down here, you see that the URL is going to be URL underscore base plus in file, what we've defined up here. You see this plus sign. All right, what happens when we do a plus sign with character strings? Well, what it does, it just sticks them together. Basically, it just takes them and glues them together. So let's go ahead and do that. So let's take a look. What is URL? All right, so if I look through here, we can see data underscore Altman, then the slash is the end of it, and then altman126.txt is the suffix of the character string. All right, And so we can see that this plus sign just concatenated the two strings together, just took them, glued them together. And this plus sign is a really easy way for accomplishing this. This is much easier than how a lot of functions or a lot of programming languages handle strings. All right, now let's go ahead and use NumPy, gen from text file. So what we're going to do, we're going to use the URL and the function from the URL lib package to request URL open. We're going to download it, and then all right. So what this does, this pulls in the data into the NumPy function, and then we're going to tell NumPy that we're separating the data by comma. So this is actually a comma delimited file. So that's really great. So here, let's go ahead and do that. All right, and just to make sure that it's doing what I want it to, oops, let's do data.head. All right, well, it's not doing well there. Oh, let's make it into a data frame. I'm embarrassed. There we go. So now let's do that. All right, so now we can see the head of the data frame. Now, so we're taking HS, fetus, and observer. Now what we want to do, we want to say that HS depends on fetus, observer, and then interaction between fetus and observer. Now you'll notice I'm putting a C around these, capital C, and then the parentheses. This is to tell it to not take fetus as, or to actually take that as the name of something and grab the value that's connected to that. And that's what this capital C open close parenthesis does. And this colon, single colon, tells the system that I want an interaction term included in this. All right, so when I build the model, what's going to happen is I'm going to have an intercept term that's implied by the formula, because there's no intercept. There's no intercept present, but there's also none removed. By default, we're going to have an intercept term included. Then I'm going to have a linear term for fetus. I'm going to have a linear term for observer. And then I'm going to have a term, I'm going to have a coefficient times the fetus value times the observer value. And then that will be our formula. So let's take a look. Okay. So now let's see what happened when we did that. All right, so we have a regression linear model going. All right, all right. So now let's go ahead and run Anova on this. So we'll get, okay. So here we can see that fetus has 2 degrees of freedom, observer has 3, the interaction term has 6 degrees of freedom, and the residuals have 24 degrees of freedom. We can check out our sum of squares. So we have 324, then a little bit more than 1, about half, and then less than 2 over here. Now the average of the sum of squares is 162.4, say 0.1 about, and then residual is about 0.1. All right, so now I'll do my F-test. So remember that when I talked about the F-test, we have to make the assumption that our residuals are normally distributed. That's important. Also, we need to make the assumption that we have constant variance on our residuals. Okay, so let's check to see what do we get from our F-test. So I'm going to take the value over here. I'm going to divide by, I'm going to divide by the other variance term, because remember the F-test is always analyzing the ratio of variances. And so we get a pretty big number. Wow, that's big. That is huge. That is super, super big. And so that is definitely statistically significant. And now over here, I say, hey, that's pretty small. But now look at this interaction term. The interaction term, I've got 0.33 as my p-value. I'm like, should we have this? I don't know. So here, from a statistics point of view, I feel that fetus and observer for an interaction term is not statistically significant. So let's go ahead and do this. Let's go ahead and remove it. See what happens. All right, so now you'll see that this p-value gets even smaller. That's just about machine accuracy. This one stayed about the same. And yeah, and the values, so the residual values grew a little bit, which will always happen. You always get larger residuals if you remove a term whenever you're doing regression. But that's okay, because now everything is statistically significant. So I feel much better about this model. So I'm looking at this and I conclude that we should not have an interaction term in our model, that fetus and observer are statistically significant, but the mixture of the two is not greater. From a data point of view, the combination of fetus with observer is not significant. So I wouldn't worry about it, including it in a model. Well, I hope that you're having a great day and staying healthy. Take care and goodbye.